Alright, hello class. Welcome to the first lecture of actual calculus material. Okay, right now we'll be talking about section 2.1 and specifically all of chapter 2 is on the concept of limits. Alright, and 2.1 is basically an introduction of that. I thought I'd start by a little introduction and motivation, of my own, which is if you consider calculus to be the mathematical study of change, okay, say for example how one quantity changes causes another quantity to change. That's kind of what limits do. All right, limits are basically a way to help us discuss the weird behaviors that we see in various functions. So a limit basically says, okay, if x gets really close to a certain value, say like 5, okay, what is the function f of x, or the y values, what are they doing when that happens? Okay, so it gives us a question. If we have, say, a function f of x, okay, a limit asks, how does f of x behave as x gets very close to a certain value? And a big motivation for this is it's essentially, you can think of it as a tool we use to talk about functions, say when they're undefined, right? Because if you think of a function like 1 over x, when you plug in 0, you get division by 0. Or say you have any function and it turns out that plugging in at 5, for example, causes division by 0, we can actually use limits to help us still talk about, okay, how the function behaves around that place where we get division by 0. All right, that's one of the big ways to talk, or big applications for using limits as far as an initial tool. Okay. But it's a concept that will actually lead us to the rest of calculus. So without further ado, let's go ahead and start with, say, the boring book definition and get to some examples. Okay, so here we are, starting with section 2.1 here. We're starting here with the official boring book definition of the limit. So here's basically what it says, and we'll kind of give it in more layman's terms after this. But basically, if we suppose the function f is defined for all x near a, except possibly at a. Okay? Now, if f of x is arbitrarily close to some L for all x sufficiently close to a, but not equal to a, okay, we say that the limit as x approaches a of f of x is equal to L. And it's denoted like this. We say the limit, it's Lim, as x goes to a, there's a little arrow there, of f of x is equal to L. Okay, so this is kind of a stuffy kind of book definition here. What we basically say, or what you really need to know about limits, is the following. Basically, that if the limit as x goes to a of f of x equals L, okay, if this is true, right, so how we talk about this, of course, is that we say that the limit of f of x as x goes to a, or we could say the limit as x goes to a of f of x is equal to L. Okay, this is true. What this is basically saying is that as x gets arbitrarily close to a, and this is on both sides, then f of x is getting arbitrarily close. Sorry about that. Arbitrarily close to L. Okay, so basically, as x gets closer and closer and closer to this value a, right? When this is happening, okay, our f of x or our y's are at the same time getting closer and closer and closer to L. Okay, so that's what we mean by arbitrarily close, that x could get as close as we want to a, and f of x will get super, super close to L. Okay, so that's kind of in layman's terms what we mean. Now, a great question here is, what in the world do we mean by arbitrarily close? I think a great way to explain that is actually through an example. Okay. So what I like to start with usually is a table. Okay. Right. And so what we're looking at here with this example is, say we want to consider f of x equals x cubed minus 8 all over 4 times x minus 2. Now here's what I was talking about before. When I plug 2 into this function, right, well, I get some weird behavior. I basically get 0 over 0, and that's undefined. Right? So, as is written right here, f of x is undefined when x is equal to 2. Okay? But as I mentioned before, limits help us kind of approach this in a different way, help us actually describe the behavior of what's going on. So that's sort of a motivating question here, right? Question is, what is f doing as x gets closer to 2? Right? That is basically what the limit is asking, right? The limit as x goes to 2 of f of x equals what? In other words, as x gets closer and closer and closer to 2, what is f doing? Right? What is f getting closer and closer to? So let's move this up a little bit, and we're going to start making a table here. Right? So we're going to be looking at our x's, and we're going to be looking at our f's. And I'm going to start looking at x's, okay, when x is getting closer and closer to 2. So I'm going to start with, say, 2.01. That's really close to 2. I'm sure you would agree, right? 2.01. Well, when x is equal to 2.01, f is equal to 3.015025, as you see. And keep in mind that this is f of 2.01. Okay. Now this doesn't tell us very much, so let's get even closer. All right, so when x is equal to 2.001, well, that's even closer to 2, right? F is going to be equal to 3.00150025. Okay, and once again, that is f of 2.001. And let's get even closer. Let's throw another 0 in there. So when I look at 2.0001, okay, I'm going to get 3.000150003. Okay, so it seems like the closer we get to 2, right, the closer x gets to 2, well, f is getting closer and closer to 3, it looks like, because it seems like every time we add a 0 over here, right, to the right of the decimal point, we're adding zeros in here. And it looks like that 15 and the 25 are just spreading further out to the right. And eventually, we put in enough zeros over here, we should eventually have so many zeros over here that that 15 will get pushed right off. So let's see. Okay, and that's what we start to see. I throw in another 0 here. So at 2.00001, I get basically 3.000015000. So, and then last one, throw in another 0. So at 2.00001, we get 3.0000015, and I mean, as we can see, that 15 just keeps getting pushed further and further to the right, and eventually, with enough zeros, we get close enough to 2 with our x's, then our f is going to get closer and closer to 3. Okay, so that's what is meant, right, by arbitrarily close, right? As x gets really close to 2, right, as we can see here, thus as x gets arbitrarily close to 2 on one side, we see that f gets arbitrarily close to 3, right? So that's what we're talking about. Arbitrarily close basically means that when I let x get so close to 2, I mean so close that your calculator would probably just round, okay, what is happening to f? What is it getting closer and closer and closer to? Right? Now, a limit isn't good enough to just check one side. We've actually got to check both sides. So, right, if you think of your number line, and here's 0, 1, 2. We were looking at this function on this side of 2, on the right of 2, right? Because we started with, say, something really close, 2.01, and we just kept getting closer and closer and closer, and maybe right here is 2.0000. Right. Well, next I need to check this side. All right, I want to see what the function is doing on the left of 2. All right, so that's what this next sheet is here. So we have this second table, and we start on the other side. So now I'm going to start at something like 1.99. Okay, and when I do that, I get 2.985025. Then I'm going to just keep adding 9s. Because basically here, we probably would have already rounded this to 2. Same as over here. But now, when we keep adding 9s here, this last one, 1.999999, we would definitely round that to 2. Right? Your calculator probably would as well. So anyway, as I start adding 9s to the right of the decimal place, right, what happens to my pattern over here is I start at 2.985 for my f's. then it gets to 2.9985. Then we get 2.99985, 2.999985, 2.9999985, so on and so forth. And here we get a similar looking pattern, right? Over here that 15 was moving to the right and we were getting zeros put in, right? Here something similar is happening. That 8.5 is being shifted to the right as we get closer to 2, but it's throwing in 9s. And eventually, if we did 1.999999, enough 9s, we'd eventually get 2 more 9s than we could fit on the table. Right? Eventually that 8.5 would shift off, we'd get just tons of 9s, and we could get as close as we wanted to 3 from what we see in this table here. Right? So on both sides, we have that as x gets arbitrarily close to 2, we see that f is getting arbitrarily close to 3. Right? Arbitrarily close, we could get as close as we want. So close such a calculator would round it if you plug that in. So close that you'd be insane not to round, but remember, we're not actually at 3. We're just really, really damn close. Right? So what we say is basically that the limit as x goes to 2 of f of x is equal to 3. All right? So if I was to graph this, right, on a calculator, I've already skipped to it, but what we have here in my y equals, I have the function we've been looking at. Remember, that's x cubed minus 8 all over 4 times x minus 2. Remember, always put your entire denominator in parentheses. And we'll go ahead and graph this. Now, if you're curious about what my window is, here's a look. Okay. And basically, remember, one thing that we have is that f of 2 is undefined, right? So we know that f of 2 is undefined. So when I look at this, from the calculator, it's very misleading because you see we have 2, 3, it looks like, the point there. Your calculator doesn't actually tell you that there's a hole there. Okay? But we know, because we checked the limit, that the graph should look more like this. Okay? Graph, and this is the point 2, 3, right? When x actually equals 2, f is undefined. That's why we have a hole here, right? Because that's because f of 2 is undefined. But, okay, and here's where the limit comes in. Even though we have a hole, we see that close by, right, close by that value, that as my x's get closer and closer to 2, right, the y values are getting closer and closer to this y value of 3. Okay. And on the other side, as the x's get closer and closer to 2, the y's are getting closer and closer to 3. Okay, so as my x's get closer and closer to 2, right? The y's are going down along here and getting closer and closer to 3. Right, so the thing to note here is that just because we have a hole there doesn't mean that the limit doesn't exist or anything. The limit is actually 3. And that's exactly one of the reasons why limits were, say, developed in the first place, to kind of help us deal with situations like this where the function is undefined at 2, but the limit itself still exists. We still have behavior. The function gets closer and closer to this value here, 3, on the left and the right. Okay, so here we have graphically that as x gets arbitrarily close to 2, f of x gets arbitrarily close to 3. Okay, therefore the limit as x goes to 2 of f of x is equal to 3. All right. So this idea of checking from the left and right, well, we can actually define our limits on the left-hand side and the right-hand side. Here's the official definition, right? I'll just leave that up here for a second. But basically what you need to know, the important part, is this is the same idea. All right, we're thinking about what happens to the function. Okay, what happens to the function as x gets closer and closer to some value a. But here it's either from the left or from the right. Okay, now the thing to note is from the right-hand side, we have this notation here, a plus, a to the plus. And how I think about this is if we're looking at, right, a limit, say, coming to a right-hand limit, we look at the limit as it comes from the right. Right, it comes from the right. So we're talking about it coming from the positive side. Right? So this is a limit from the positive side. Right? From the positive direction, right? Because that's over here. And for the left-handed limit, well, it's the exact opposite. You see that its notation, it gives us a to the negative side. And those limits, right, if say we're coming from, or looking at as x goes to a, that will be coming from this direction. So this is a limit from the negative side. So if you see a limit where, say, you have a plus sign or a minus sign, and you got to be really careful because it's to the power. Don't mix this up. We can still have a negative number, but with a positive exponent, so to speak, right? Or a negative number with a negative exponent. That just tells you which direction are you looking at. Okay, so, oops, sorry. So, for example, here, this limit as x goes to a, so this right here, you can't see that, this right here, that's the number we're looking at. okay? Specifically x values. Okay, so we want x gets closer and closer to a. And if we have a plus or minus up here, this tells us the direction. You can see that. Okay. This tells us the direction that we're coming from. And that makes it easy to read. Okay. So positive means from the right. Or positive side. That's how I always keep this in my head. It's from the positive side. And if you have a negative side, it's from the left. Right, that's the negative side. And then f of x you have to have there. Okay. So this is a great time to tell you all that when you are calculating limits, or when you're writing about limits, okay, you can't ever just put, say, the limit as x goes to 5 equals whatever. You have to have a function you're looking at, right? Because the whole point of this stuff is that as x gets closer and closer to 5, what is f doing, right? We need that question to be able to ask it, right? We need that function to ask about. You know, what is happening as x goes to 5? What is happening to specifically f, right? So that's definitely something to keep or be aware of. Get some of this stuff out of the way. And let's look at this example here. So let's say that this guy is f of x. Okay? So f of x acts kind of crazy, right? It has this little swoop down, and then it's got a jump. So it's got an open dot here, right, up at 2, 4. It's got a closed dot here down at 2, 1, and then it continues its descent downward. So it looks like a quadratic up here, it'd be linear down here. Okay. So here's the question that I'd like to ask about this is what is the limit as x goes to 2 from the right of f of x? If you can read that. Make sure this matches. Okay, so remember, students tend to have trouble with this, and I think a lot of them are just making it a little more difficult than it needs to be. First, where are you looking at, right? You need your x value. So your x value is definitely this 2, right? Then what direction are you coming from? Well, positive means you're coming from the right, okay, from the positive side, right? So first we go to the x value we're looking at. That's right here. We're looking at x when it gets closer and closer to 2. Now, this guy is from the right. So what I like to do is when I first learn this stuff, okay, the x value is right here. We're looking at different y values, and we're concerned with what is happening as x gets closer and closer to 2 from the right. Right? So I don't care about the left side. So because of that, what I tend to do is I take a sheet of paper and cover up the left-hand side. And then I look to see what is happening as my x's get closer and closer and closer to 2. Right? So each little tick mark I made here corresponds with the point up here on the graph, and it looks like that as x gets closer and closer to 2 from the right, these points on the function get closer and closer and closer to this point right here, right? Which is the y value 1. Fair enough. So as x gets closer to 2 from the right, okay, our f of x gets closer to 1. So the limit as x goes to 2 from the positive side of f of x is 1. Okay. Similarly, if I want to look at the limit as x goes to 2 from the negative side, f of x. Okay. So this, remember 2, that's the value I'm looking for, right? The x value I'm looking for. Sorry, seems my camera decided to turn itself off. So the x value I'm looking at here is 2, and the limit is going to tell me what the y's are doing. So, and since I'm looking at from the negative side, that's the left side, right, I'm going to cover up the right side and then take a look at what the function is doing. So, remember I'm looking at 2 here. So as my x's get closer and closer and closer to 2 from this side. Now a lot of people like start all the way over here. Remember, limits are, you're looking at what's happening as x gets closer and closer and closer, arbitrarily close to 2. So you actually want to see what's happening really, really, really close to 2. Right? And so as that happens, each little tick mark I drew as the x gets closer and closer to 2 corresponds with a point. It's closer and closer and closer to, it looks like it's getting closer and closer and closer to this open dot here, right? These points along the y's are swooping down to hit this open dot here, which corresponds with 4. Okay, so as x's get closer and closer to 2, okay, from the left-hand side, okay, it looks like the y's are getting closer and closer and closer to 4, since if we map these points over, right, they're getting closer and closer to 4. So the limit as x goes to 2 from the negative side of f of x is 4. Okay. So, let me move this up a little bit. What could I say about now the limit as x goes to 2 if I don't have a plus or a minus? Well, if I have no plus or minus, this means from both sides. Okay. Oops, and I'm not following my specific rule here. So the question is, what is this, the limit from both sides? Okay, so the limit from the right we found was 1, you can see that, and the limit from the left was 4. Okay, well, what do we say? Well, the answer is basically that the two-sided limit here does not exist. Simply does not exist. Okay, so that brings us to our next concept. Which is the following. Okay. That basically the only way a two-sided limit can work, remember two-sided limit, that's our usual limit. Our usual limit is a two-sided limit. Okay? And basically the limit as x goes to a of f of x is equal to L if and only if the right-sided limit is the same as the left-sided limit. Right? So this is from the right-hand side. This is from the left-hand side. And if they're both equal to L, that's the only way that the two-sided limit is going to equal L. So in other words, the limit of f of x as x goes to a is equal to L only when the left-hand limit and the right-hand limit both equal L. Okay? So if the left and right-handed limits equal two different values, in other words, say from the right it equals L, from the left it equals M, then we say that the limit as x goes to a of f of x does not exist or is undefined. We often use this shorthand D and E for does not exist. Okay. All right, one thing I wanted to definitely mention very quickly is if we go back to this example here, right, and I'll erase some of this stuff. Okay. Now we talked about the limit. We know that the limit does not exist, but if I were to want to find maybe f of 2, so if I went to actually plug in f of 2, well, remember we go to where the closed dot is, right, which is 1. So the function actually has a value at 2. It's equal to 1. But the limit does not exist. Right? So what I wanted to basically say here is that note in this example, so note that f of 2 is equal to 1. Okay. But the limit as x goes to 2 of f of x does not exist. So these two things do not have to intertwine. So that was this example, but in the previous example, right, we had the complete opposite situation. Right, we had that f of 2 does not exist, right? It was undefined. Whereas, right, the limit as x goes to 2 of f of x actually ended up being 3. Okay. So whether the limit exists or not is completely independent on whether the function exists. Right? They're two completely different ideas. This is when x is actually equal to 2. Right? Huge difference there. Whereas the limit That's telling you what happens as x gets really close to 2. Okay. Big differences there. Okay. So that's sort of like if you were on a graph, right? This point would actually be f of 2, whereas all the values, say, that are getting the behavior of the graph around that point, right? What's going on around there is the limit as x goes to 2. Okay, that's a really important concept to understand. All right, so let's look at another example that uses a graph. Okay, we'll probably hit just about every possibility here. Hopefully. Okay, so here we go. We have the graph of f of x here. And we're going to use it to evaluate some various problems. So say, first of all, I want to find the limit as x goes to -2 from the negative side of f of x. Right, so this 2 to the negative. So first, -2, that's the value I'm looking at here. Right, so we go down here to my graph and we mark off -2, which is right here. And this negative means that we're coming from the left. So this is a left-handed limit. Okay? So from the left means we're coming at it from this direction. Right? So from the left. Okay? And remember, when we do this, we don't really care about the right. So I can actually cover that up. Okay. And now I'm going to start. Now remember, we want to get really close to -2. So -2 is here. This is like -2.5. Right? And we want to get even closer than that because -2.9 might be like right here. Okay, -2.999 is like even closer. So I suggest starting about halfway through, but that's not even close enough. Really, you want even closer when you start looking at what's happening here. Okay, so as the x's get closer and closer from the left, it looks like the graph, right, is moving along and getting closer and closer to this open dot here, right, which maps us back to 3. So as the x's get closer and closer to -2, the y's are getting closer and closer to 3. So the limit as x goes to -2 from the left is 3. All right, this next one is basically just asking the same thing, but from the right. All right, the limit as x goes to -2. Right, so -2, that's the number we're actually looking at. The positive means from the right. So same x value, but now we're coming from the right-hand side. So I will cover up the left-hand side. Okay. And remember, so if we started about halfway through, this is about -1.5, and say I did misspeak last time. I think I said 2.9 over here. That's supposed to be 2.0, 2.1, stuff like that. Here is -1.99. I apologize for that. So we want to get closer and closer to -2 from the right. So as we do that, we map this up, and it looks like the y values are getting closer and closer to this open dot here. Okay. So removing this, we see that, oh, that's 3. So the limit as x goes to -2 from the right is also 3. Okay, so for the next bit, now it asks the limit as x goes to -2, and it doesn't give us a direction, right? No direction. So that means from both sides. So from both sides, well, from the right, it was going to 3. From the left, it was going to 3. They match. Therefore, the two-sided limit is also 3. Okay. All right. How about f of -2? So this is when x actually equals -2. And when x actually equals -2, we go to wherever we see the closed dot, which is right here, which ends up being -3. Okay? So we don't actually have to have the function value and the limit match, right? It just helps. Okay. All right, my battery's starting to die here, so hopefully we can finish this up before that happens. Okay. Let's look at this next one. We're looking at the limit as x goes to -1 from the negative side. So -1 is the value we're looking at. So let's go ahead and erase this stuff. Okay. And that negative means we look at it from the left. So I'm not going to cover it with paper this time. I'm just going to say, okay, so -1 is here. We're going to start maybe here, -1.5, and get closer and closer and closer to, say, -0.001. And when we do that, we map upwards. These points get closer and closer and closer to this point here, which is 2. Okay. So the limit as x goes to -1 from the left is equal to 2. Okay. How about from the right? That's the next question. From the right, well, -1 is here. We're going to start picking our x values around here, say at -0.5, and get closer and closer and closer from the right. As that happens, these points seem to be getting closer and closer and closer to this point here, which rests right at the y equals 0. Okay. So it looks like the limit as x goes to -1 from the right is 0. Right? As x gets closer and closer, what are happening to the y? So the y's, when we map them over, get closer and closer and closer to 0. What about the two-sided limit, right? The limit as x goes to just -1 from both sides of f of x. Well, since the limit from the left was 2 and the limit from the right was 0, they don't match, right? Because up here, they matched. Here, they don't, so the limit will be, does not exist. right? And how about f of negative 1? Well, to find f of negative 1, we just look at negative 1 and see where the open dot would be, and that's right here at 0. Okay? So here's a place where the function value actually exists, but the limit does not because we have a jump. And our final two questions here, final two ideas. Let's take a look at the limit. And let me write here, for this one, this is when x actually equals negative 1. Here, I want the limit as x goes to 2 of f of x. So we're starting right at both sides. So some problems are just going to take you through each step, like check the left, check the right, now check both sides. This one is just, hey, check both sides. Okay, so here we're at 2. And it's kind of nice. We don't have any jumps. We have a nice continuous function here. So if I check from the right, because here's 2, so if I start checking here and map down, we can see that the function gets closer and closer to this value right here, which is negative 1. Okay? And when I check from the left, so if I check maybe here, we're checking close, when I map these values down, well, they get closer and closer to this value 1 as well. Right, so I get out negative 1 from both sides. Okay. Now f of 2, this is when x actually equals 2, and I kind of messed this all up, but when x actually equals 2, that's this point right here. And alright, my battery almost made it. So, as I was saying here, when f of 2, or when x actually equals 2, we get that f of 2 is equal to negative 1. And this is a case where the limit and the function value actually match. And we didn't get that in these previous examples. Right? In these previous examples, well, either the function value didn't exist, but the limit did. That's a nice little hole there. Or here, the limit didn't exist, but the function value did. This is a jump. And then here we had the limit and the function both existed and they matched. And that's at this nice little place here where the function is continuous. There's no holes, there's no jumps. This is kind of a this kind of spoiler alert, right? That eventually we're going to learn that if a function is continuous, right, its limit is going to match its function value. Right? If a function is continuous, then f of 2 is going to be equal to the limit as x goes to 2. Okay. All right, so that is that example. Let's go on to talk a little bit more about some function properties and whatnot. Right?